What's up, everybody? It's Dr. J, and yes, today, we are still talking about chemistry. So today's video, we're talking about activation energy. Okay. All right. So let's talk about activation energy. All right. So activation energy. If we look down here at this equation, say we got hydrogen and oxygen reacting together to form water. All right. So when we're thinking about activation energy, let's look at this graph here. So we got our energy on our y, and then the reaction going on the progress on the x axis here. So when we start off right, we got to understand that with our energy of our reactants, so we're talking about hydrogen and oxygen here, is that they start off at a certain energy level. So they at this level here. And as we go on through that reaction, right, over time, we're going to reach this peak in energy, right? So the reason why we're reaching the peak in energy is because this is what we call the activation energy. All right, so this activation energy is needed in order to convert our reactants to our products. Okay, that's what we're seeing here. So we're seeing this energy being raised, right? Activation energy, and then it's going to form our products, in this case water. So what you need to understand is basically, right, due to the bonds, right, that we mentioned before, we understand that, right, these products, once they form, they're going to be more stable. All right, so since they're more stable, they have lower energy than our reactants. Okay, but we need that activation energy in order to get to our products here. So that's the reason why activation energy is so important. All right. So we can actually calculate our activation energy by using Arrhenius equation. Arrhenius equation is K equals AE to negative EA. That's like EA Sports. I remember that? EA Sports. All right. Anyway, negative EA over RT. So let's talk about Arrhenius equation, like specifically what these things even mean, right? So K, we understand that K is still going to be our rate constant, so that should look familiar. But let's talk about A here, right? This A. So A is what we are calling our frequency factor. So basically the frequency factor is the number of times a reactant will be approaching that activation barrier, okay, per unit of time, okay? So basically, right, with this activation energy, we have this barrier because we got to understand, right, it needs all this energy, but sometimes stuff ain't just able to get all that energy, right? They might be like, oh, it doesn't make it. All right, so this is that frequency factor, the number of times a reactant approaches that barrier, right, in this case, right, to get over that barrier to form that product. All right, so that's what we're talking about there. EA is the activation energy. Okay, so once again, this is the activation energy, like I mentioned before. So this is, by definition, the energy barrier that must be overcome in order for reactants to transform to products. So like I mentioned before, you must have activation energy, all right, to form our products here. That's all it is. All right, we need that energy to get our products here. T is going to be temperature. So remember, we're talking about temperature. We're talking about kelvins. And then R, that sounds familiar. It is because that's our gas constant. In this case, it's going to be 8.3 to joules over Kelvin mole. Okay, so that's our gas constant. You notice something, right? All right, so we have Arrhenius equation to help us find activation energy. But what we have to realize is that, well, Arrhenius equation ain't just going to give me the activation energy easy, right? We can see that it's going to be raised to E. And if y'all forgot, E is not mentioned on here. That's because it's a constant, all right? So that's, y'all remember that in math class, right? E is on a constant. If you look at your calculator, they got that little E button. So that's what that is there, okay? So, Dr. J, how am I supposed to solve for activation energy? You got to do some algebra. What I tell y'all, I told you, chemistry is math. But, Dr. J got your back. You got to do the ln, right? K over 2, K1 equals the EA over R, 1 over T minus 1 over T2. Now, I'm not going to really go over the math side because we're just focusing on using this equation. But if you know how to do math, you could have literally solved for this on your own. Like I said, everybody, chemistry is math, so you just got to do some algebra here. All right, but basically, let's look at this equation. So this is our final equation. So if you need to solve for activation energy, you're going to use this equation here. So take a picture, write this down, definitely right now. EA equals R, so that's our gas constant, times Ln K2 over K1 over 1 over T1 minus 1 over T2. If you use this equation, you will be able to solve for activation energy. Okay. And if you don't need to solve for activation energy, right? For instance, you need to solve for something else, temperature or the frequency factor or even the rate constant. You'll use this Arrhenius equation here. Okay.